Welcome to your Daily Dopamine with Dr. Joe McCullough, where we deliver daily doses of education, entertainment, and inspiration.
Did you record this yourself?
Relax.
No, I Fiverr purchased. All right, welcome. Having a bit of technical difficulties. My selfie stick tripod just broke, so we're trying to rig something up in the lab. Hey there, Lily Blue, welcome. And I keep looking at the wrong place. The camera is right there. So today is Physics Wednesday, Ask a Physicist Anything with...
Hey there.
So we are here to have some interesting discussions about physics. Last week, we had a question about special relativity that we didn't get a chance to touch on. So I think we're going to start with a little bit of relativity. So you actually want to give a quick little 2-minute, what's the difference between special and general relativity?
Okay, well, special relativity was the earlier and more limited version of Einstein's relativity.
Hey, one quick thing. Have you seen the show The Big Bang Theory?
I haven't.
Okay, neither have I. Somebody wants to know about how accurate is the show The Big Bang Theory. Unfortunately, neither of us have watched it, although I've been told by many students that I should watch it.
All right, the special relativity. 1905, when Einstein first came on the scene, he was this obscure Swiss patent clerk just out of college, published 3 papers that rocked the world of physics, all in the same year, 1905. And one of those 3 was a pretty much complete version of what we now call the theory of special relativity. Now, the reason you call it special and then general relativity is general, the way mathematicians use those 2 words, it is almost the reverse of what you'd expect in regular English. I mean, if I say, well, you know, I don't like broccoli. Actually, I do like broccoli. But if I say I don't like broccoli, and then you start pressing me on the issue, and I say, well, in general, I don't like broccoli. Well, it sounds like I've just weakened my stand on broccoli. It sounds like I'm, open to admit there's exceptions or something.
Real pause. That was a real picture of Einstein sticking his tongue out. It was not photoshopped.
Totally.
There's lots of fun pictures of Einstein.
But if you talk to a mathematician, if they say something's true in general, they're not weakening their statement, they're strengthening it. They're saying, this is true in a much broader case of circumstances. You could say they're saying there's no exceptions, but like when we say general relativity, we're not actually saying it's true under every possible physical circumstance, but we're saying that it takes into account a lot more possibilities than special relativity. In particular, general relativity, whenever you see those illustrations of how the existence of mass, or actually of any form of energy, pulls space-time into a curved configuration, and will show you a 2-dimensional sheet, usually with grid lines on it, and you pull it into a funnel near a black hole or a neutron star or something, that is general relativity, because the basic thing that general relativity includes, that special relativity doesn't, is this idea that space-time is not a flat manifold, it's a curvable manifold. That space and time themselves are players in the game of physics, not just a passive arena where the game takes place. And you can tweak the shape of space-time and it'll spring back. And as I'm miming kind of, pulling space-time down and letting it spring back, well, if I were an octopus and I could kind of keep this pantomime going, then I would be showing you gravitational waves rippling outward from the point where I let that space-time energy be released. So in other words, the arena itself, space and time, is a participant. You can stretch it, it'll spring back, it's got a dynamics of its own.
So general relativity really has to do with space-time, curvature of space-time.
Yes.
Not only, but that's the big thing.
And it is also the most accurate model we've got of gravity, because it turns out that what we call the force of gravity, what Newton would have called the force of gravity, is just kind of a side effect almost of that curvature of space-time. Once you've described the curvature of space-time, you have described gravity. You haven't just described the arena that gravity plays out in, but that's what gravity is the effects of this curved space-time.
Okay, now touch on special relativity.
Okay, so special relativity. For this one, I am not going to talk to you about black holes and neutron stars and all that, because all of those space-time stretching, really dense masses are the domain of general relativity. Special relativity just deals with some peculiarities people had noticed about motion. In particular, there was a couple guys named Michelson and Morley in the 1880s who had done a set of experiments. I'm not going to go into the details of how they set up these interferometers that they used for their experiments. I'll tell you what their conclusion was, though. Their conclusion was if you chase after a light beam, it is still going just as fast relative to you. Now, what do I mean by that? Okay, suppose you're chasing a bird. Here's a bird flying through the air at 40 meters per second. By the way, that is about almost 90 miles an hour. So we're talking a really fast bird here. I've got a...
Somebody says they love you. You're so enthusiastic. Is he not? This is why I wanted to do this whole Ask a Physicist Anything, so I can hear Paul go off on physics every week.
The universe is awesome. Who could not be enthusiastic about it? But so you're standing here in a car and you're chasing that bird, and if you've got your car going 30 meters per second and the bird's still doing 40, then you'd think that as measured by the person in the car, they're going to say the bird only seems to be passing them at 10 meters per second. In fact, if the person in the car wants to say, hey, I'm going to make all of my measurements with respect to the car. Look, I even carved some XY coordinates on the side of my car. And anybody who does that as soon as they buy a new car, I want to have a beer with you. That's the sign of a true physicist.
Team Paul, Team Joe, Team Physics. Yes.
So our driver's carved XY coordinates on the side of her car, and she says, all right, that to me means now this guy who was standing by the side of the road before making our old measurements, he used to claim his velocity was 0, and my car was doing 30 meters per second, the bird was doing 40. Well, nah, she says, nah, his velocity is 30 meters per second that way. Mine is 0. She says her car is doing 0, and the bird's doing 10. Now, this was a radical idea when Galileo proposed it. We call this now Galileo's version of relativity. So the idea that there is a principle of relativity, that there's no one right reference frame to measure your velocities from, that was an important departure from that old Aristotelian view of physics, and that was one of the big things that Galileo argued for in his lifetime. Now, the problem is, this works great, by the way, for birds and pedestrians and cars who are all moving at baseballs,
anything not
trains,
going super fast.
anything moving at a small fraction the speed of light. This works almost perfectly, so much that they had never noticed any flaw in this Galilean logic at all.
One quick little pause. We are talking about special relativity, and Paul's giving a little overview about what special relativity says, and then hopefully we'll touch on what happens when we start approaching speeds near the speed of light.
All right, so now we've got our passenger in the spaceship doing something a little bit more ambitious here. She still zoomed right over the head of this observer out here. This time, suppose she was going 80% the speed of light. And suppose she sees a photon go by overhead. And according to our stationary guy on the platform, the photon's going exactly the speed of light. By the way, that speed that I'm abbreviating there is c. That's one of the fundamental built-in constants of the universe. It's roughly
3 times 10 to the 8 meters per second, 186,000 miles, not an hour. 186,000 miles per second.
Yes, light
the
goes
ultimate
around
speed
the
limit in the
circumference of
universe.
Earth 7 times per second. So our spaceship pilot is now chasing down that light beam. And again, if we were to use Galilean relativity, we would assume that if you ask her how fast the light beam's going, relative to those coordinates that she has carved on the side of her spaceship, well, common sense told people the pilot should see that light beam going at 0.2 c. And she should see the guy on the platform doing 0.8 c the other direction. In other words, people assumed that Galilean relativity was just built-in common sense about the way space and time worked. How's that for a change? You spend your lifetime coming up with really radical ideas, and eventually your unimpressed descendants just kind of think, well, of course, it's common sense. Everybody knows that. So by this time, instead of thinking Galileo was some radical nut job who had been trying to overturn the Aristotelian hierarchy, they said, no, of course, this is the only way space and time could work. And Michelson and Morley tried it. They did not hire a spaceship pilot to go 80% the speed of light, because technology didn't allow that. Still doesn't today. We can't go that fast. Human-sized things can't go that fast. We can get subatomic particles going that fast easily, and we do, and
every
we study
day
their motion. But what Michelson and Morley did was, for the spaceship, they used the Earth. They said the Earth is orbiting the sun, and yeah, we're not going anywhere near the speed of light, but were going fast enough that with a really sensitive interferometer, they were certain they would be able to detect that the light was moving a little bit slower as it overtakes the Earth in its motion through what they called the ether at the time. And the light would seem to be going a little faster relative to us if we pass it head on. Same reason that the traffic in the opposing lane seems to be going faster relative to you if you pass it head on the freeway. On the other hand, if you're looking at somebody who's going the same direction as you, they're passing you or being passed really slowly because, again, you know, this Galilean relativity is at work.
All right, so, Paul, move your head for 1 sec. Somebody wants to take a quick screenshot. If you want to take this down, just press the home button and the power button at the same time. All right, continue, please.
So this is what Michelson and Morley expected.
Quick question, what % of the speed of light can we go? Subatomic particles all the time are going at 99.99% the speed of light, some of them. Yes. What would you say the fastest...
fastest human-powered vehicle?
Yeah.
Well, the Apollo astronauts made it to the moon in a few days, right? And that's 750,000 miles, so a little over 100,000 kilometers. 5,000 kilometers an hour. If you're orbiting the Earth, you've got to be going about 16,000 miles an hour just to, you know, for
still
low
tiny,
orbit.
tiny. So 16,000 miles an hour compared to 186,000 miles per second.
So that
we're
is
going a
about,
small fraction.
Yeah, about 1/40,000th the speed of light.
Yeah.
So, you know, I didn't say 1/1,000,000th or something like that. 1/40,000th. We're making progress. But yeah, a human-sized spaceship, we can't get going anywhere near the speed of light. Now, if that makes you think, hey, relativity is still this radical, untested model that's never been tried out. No. Since we can get subatomic particles moving close to the speed of light, and since relativity isn't just about aging and time dilation and all the things we like to say, but it's got a whole new set of rules of motion, replacements for Newton's laws of motion. So if you're running that particle accelerator, and you speed up your beam of particles to almost the speed of light, and then you've got to steer them around that curved track to get them to the collision point, hey, you got a choice. You could try to use Newton's laws to calculate how those particles will steer around the track, how they'll respond when you apply electric and magnetic fields to them. You could try to use Newton's laws. You will get absolutely the wrong answer, and your particles will crash into the wall of the tunnel and never make it where you're trying to get them. On the other hand, you can use special relativity to try to calculate how those particles behave at nearly the speed of light. And it works. It works beautifully. Again, we don't think it's perfect. We think at out to enough decimal places, you might find a discrepancy. And if you ramp the energy way up to energies that haven't been seen since a very, very tiny fraction of a second after the Big Bang, we think that eventually special relativity, general relativity, quantum field theory, these all have to break down and turn out to be low energy limiting cases to some deeper model yet. Now, we don't know yet what that deeper model might be, and I just ducked in case there was a string theorist off on the side of the room ready to throw something at me. Because,
I had a quick question, Lily. Were we always interested in physics? I can speak for myself. I hated physics in high school. Let me just turn this around and say hi. As much as I hate to admit it, I did not like physics in high school. I had a high school physics teacher that was way past his prime, didn't transmit any joy or excitement in the class. I started off as a biology major, going to go into biomedical engineering, took an astronomy class at night that I completely fell in love with astronomy, decided to go into astrophysics, physics. So I was not always interested in physics. In fact, I first thought it was boring because I didn't have a good teacher. Paul, you?
I had an awesome physics teacher in high school, and by the time I was applying later that year to colleges and stuff, I was already just absolutely certain that I was going to be a physics major. And it kind of surprised me looking back, saying, wait a minute, all my college essays and shit were about being wanting to be a physics major. Apparently that class won me over that quickly. I mean, there was just no doubt in my mind. So you want Neil Mackey, if you're out there in our audience, thanks, man.
Thank you. So do you want to talk a little bit about just time dilation? Because I think that's the most interesting thing for people in terms of special relativity.
Right. So what Michelson and Morley did when they tried this is they did not get this result. No matter how fast you are moving along as you try to chase after a light beam, you don't measure that the light beam is now overtaking you more slowly. You measure that it's still overtaking you at the same speed as before. The guy in the platform sees this light beam moving at 3 times 10 to the 8th meters per second. The pilot of the spaceship, even though she's zooming past the platform at almost the speed of light herself, also measures that light beam to go in that exact same speed.
And if somebody were coming the opposite direction at 0.99 c, they would still measure the speed of light to be c.
Exactly. Galileo would expect that they would, measure it to be going faster than c. They would also be measuring it to be going c. Now, to most of the physicists at the time, to their credit, they didn't just kind of, sweep this result under the rug and say we don't understand it so it doesn't exist. No, they said we must be fundamentally confused about the way light works. Now, Einstein was the only one who said, no, this is not about light. Light might be the symptom. What we're fundamentally confused about is the way space and time works. I don't care what the internal bells and whistles that make a light wave go are, but if the guy on the platform says this light beam is barely crawling past the spaceship because he's measuring him to be going almost the same speed, and the pilot of the spaceship is saying, no, that light beam just passed me at a much higher speed, they're not disagreeing about light. They're disagreeing about the amount of time that passed between two events, the amount of distance between two events, or both. So
Einstein's thinking was basically if everybody everywhere has to measure the speed of light to be exactly the same value, and speed is just distance divided by time, then perhaps our concepts of distance and time need to be altered a bit.
And the first thought experiment he came up with to calculate exactly how those things need to be altered was this. He said, let's go back to our spaceship. I'll zoom in on it here. Here's our pilot standing on board the spaceship, and she does an experiment where she's going to send a beam of light from the floor of the spaceship to the ceiling where it will click a little timer. Now, this was 1905. I mean, you notice this had been 20 years since the Michelson-Morley experiment. People had been confused for 20 years and barking up the wrong tree, thinking that if they could refine their understanding of light and electromagnetism well enough, they could explain those Michelson-Morley results. So, but even in 1905, you couldn't actually run this experiment, but Einstein said, no problem. Michelson and Morley ran the only experiment we needed, the one that says every observer is going to measure this light beam to be going the same speed. So they said, okay, here's this pilot of the spaceship. She says, all right, the height of the spaceship should be the speed of light times the amount of time that light beam took to travel up there. Distance equals speed times time. You notice, this is not even high school algebra here. A lot of the math that goes into special relativity is very simple math. High school algebra and the Pythagorean theorem will get you through most of it. This might be where Einstein got that reputation that some people like to claim.
So just pause for a second, because that's a really cool point. You can derive much of relativity with just trigonometry and algebra. And
yes.
In fact, we do this all the time when deriving the equation for time dilation. I mean, think about this. Relativity can be derived just using some trigonometry and some algebra.
And the people who had been trying for 20 years to understand the Michelson-Morley experiment, this means they had not been stymied by the lack of the needed mathematics or anything like that, which we sometimes think might be the case in string theory. They had all the math they could have needed right at their fingertips. They had been asking the wrong questions. They had not been thinking that space and time needed to be rethought. They had just been thinking that electromagnetism and light needed to be rethought. Okay, so what did Einstein say? He said, here's the person on the spaceship. Photon goes up, height of the spaceship equals speed times time, no problem. But here's what that experiment looks like to that guy on the platform. Remember, to him, that spaceship is passing by at almost the speed of light. I'm just using 0.8 as an example. So to him, the photon was emitted. Yeah, it tripped the detector on the ceiling, but by the time it got there, the spaceship had moved over by quite a distance. So he says that thing went that diagonal distance. You notice, and Pythagoras would agree, obviously the height of the spaceship is a shorter distance than that diagonal, which is going to be the square root of blah, 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 height squared plus distance squared times time squared, but I don't even really care about that right now.
Hold on one second. How can we get in touch with you? So many questions. Jessica, send me a tweet at Dr. Joe McCullough on Twitter, and I will start collecting questions, and then every Wednesday we're here. Let you all answer them.
We should give out kind of like a variety of contact information, so I'll get that together, but yeah, that'd be great. But So here we go. This time, the thing goes that longer diagonal distance. It's a longer distance than the height of the spaceship. So that's still got to be speed times time. Well, hey, what happens in Galilean relativity? Well, same thing. If I'm walking by, or you're watching me ride by in a train, and now I'm not talking the speed of light, I'm talking an ordinary everyday train. I take this pen, I lift it up 1 meter, I set it on the shelf, and I would say, yeah, the distance it traveled is the speed I'm lifting it times time. Only you're watching that from the sideline. Hey, how good are you at panning the camera, Joe?
I'll pan it. Go for it.
Okay, you're watching this from the sideline. I lift this same pen. Well, you notice it goes that much longer diagonal distance, but for ordinary everyday speeds, you'd say, okay, that's no problem. The pen went a greater distance, but it was moving a greater speed from your point of view because it had that horizontal component as well as vertical. And you'd say the amount of time it took was still the same. Doesn't matter if you're with me on the train or if you're watching from the sidelines. In Galilean relativity, the amount of time that pen takes to reach the shelf is the same. Einstein said, though, hey, if the pen's a light beam, we don't have that luxury. The guy watching this spaceship from the sidelines sees the light beam move that diagonal path, so it's definitely a longer distance. I'm going to do a trick stolen from Paul Hewitt, who writes our conceptual physics textbooks here, and just say, okay, I'm writing distance in a larger font now than I did before. So he sees that thing go a longer distance. He cannot say that it's going a faster speed. That's what we would have normally done, but Michelson and Morley have already tested it. Light waves go the same speed no matter who measures them. So instead of increasing the speed, I got to use the same speed as before. How am I going to explain a bigger distance on this side of the equation? I've only got one option left. As measured by the guy on the platform, a longer time had to pass between those two events. Now, this phenomena is called time dilation. Did I just say phenomena plural?
I don't know.
This phenomenon is called time dilation.
So in like a quick, if you can, 5 minutes, what does time dilation mean?
It means that if you are riding on board a moving vehicle, like the pilot of that spacecraft, time is actually passing slower for you. And I mean that literally. Less time passes. If this pilot does a journey that takes her 25 years as measured by the guy on Earth, so she departs from Earth, travels to some star 20 light years away that way, comes to a stop at that star, and those of you who are kind of trying to check me for compliance with the twin paradox, note that I did admit that she accelerates as she comes to a stop at that star, but comes to a stop at that star, and you ask both observers, how long did this take? To the people who remained at rest during this whole trip, her colleagues back on Earth, her colleagues who were waiting for her to arrive at that star, they all agree this trip took 25 years. You ask the pilot of the spaceship, or anybody who was on the ship with her, or any measuring device that was on the ship with her, or a plant that was growing and making growth rings, any way of measuring time, they are all going to agree that 15 years passed on board that spaceship. So the amount of time that passes between two events is not actually a universal, unalterable thing. Depending on how you are moving through space-time, you can actually measure a different amount of time between two events.
And somebody had a question. You cannot reverse time. So as far as we know, time always moves forward. But the key part about time dilation is time doesn't move forward at the same rate for everybody.
Yes.
If somebody is moving, does Paul have a Twitter? Paul does not. Do you have a Twitter?
I don't. I'm technologically illiterate.
Let me
think the easiest way to actually get questions. So I archive all of my daily periscopes on my YouTube channel. So if you search for YouTube for Joe McCullough, I've got, almost like 80 videos up there now. But I have them categorized in different playlists. I have a playlist simply called Ask a Physicist Anything. So if there's a question you have and we didn't get a chance to touch on it, check out my YouTube channel, leave a comment under Ask a Physicist Anything, and then we can touch on that next week. In fact, that might be a great way of answering any questions or asking questions. So we've got 5 more minutes. Electric transfer possible.
Electric transfer.
I'm not quite sure what that's asking. If you want to ask that again, let me turn this around.
Relativity.
Okay.
Go!
So more about relativity. Okay, so we have established that the amount of time that passes can depend on who's doing the measuring. Now, by the way, those of you who are sharp on the uptake, or just those of you who have thought through this issue before, are going to say, hey, but wait a minute. The whole idea of relativity is there's no right reference frame to do these measurements from. So the pilot of the spaceship, didn't she have every right to say, no, wait a minute, I told you. I put XY coordinates on the wall of my spaceship, and I've got a clock on board my spaceship. Position, time, I'm going to measure all these things with respect to my ship, not with respect to the outside world. And what that means is I am not moving. It's the people on this platform who are moving at point 8C in that direction. So she seems that she should have every right to say, all right, fine, special relativity is a thing. Moving observers experience less time. Time passes slower in a moving reference frame. But in that case, I'm the stationary reference frame. If this trip took 15 years for me, it should take less than that. In fact, if you run the calculation for a speed of 0.8c, and by the way, if you say, run what calculation? The time that passes on board that ship compared to the time that passes on the platform is slower by the following factor. It's 1 minus the fraction of the speed of light that you're going squared. And if that looks hauntingly like Pythagorean theorem, you are absolutely right, it is. It just comes from using Pythagorean theorem to calculate the length of that diagonal right there. The minus sign is because we've shifted terms around between the two sides of the equation while doing the algebra. But I mean, when I said this is high school math, I meant it. Einstein was not mathematically untalented, by the way. That's a myth that has grown around him. But part of the reason for that myth might be that one of his greatest discoveries, this one, really could be done by somebody who knows no math beyond their high school algebra class. General relativity, on the other hand, is mathematically daunting even to people today. So, general relativity is where he established, no, I am not incapable of doing some serious mathematics here. So the pilot says, if 15 years passed for me on board my spaceship, by that calculation there, she says, hey, it should have only been 9 years for my colleagues back on Earth. And 9 years for the people on that destination planet that's moving toward me. And notice, she'll say the planet's moving toward her, not that she's moving toward the planet, because, hey, she's standing still. She's already decided that. Her spaceship is standing still.
Can we, we're going to kind of wrap it up,
Okay.
but there was sort of a question about what if they meet. Do you want to just set up the twin paradox, and then we can start with that next Wednesday?
Okay, well, yeah, I mean, the twin paradox is essentially what we've got here. The twin paradox...
How about if we have like somebody who's on the Earth, somebody who's on a rocket ship,
Okay.
talk about the different frames of reference.
And in the twin paradox, we actually say these two people are twins. That part is actually not necessary.
But you got twins who were on the planet.
Yeah.
One of the twins stays on the planet, the other one gets in a rocket, goes off on a long journey going 0.8, 0.9, 0.99 times the speed of light, then returns.
And turns around.
Returns back to the Earth, meets the twin. The question is, who is really going to be older?
Now,
Each twin is going to think the other person is the one that aged less.
Yeah, so the paradox,
Mercury
the person who
retrograde.
stays on the planet the whole time has an easy calculation. He says, look, I was sitting here, my sister was moving, definitely less time will pass for her. I will age 25 years, she'll age 15 years on board that spaceship. The pilot of the ship, though, seems to have every reason to say, no, my spaceship was not moving. I'm using it as my reference frame. It's Earth that was moving. It receded that way for the first half of the trip, then it came back. So she says, fine, the trip takes me 15 years. It should take less than that for my brother. If we were both 40 years old when we started this, when we get home, I'll be 55, he will be a sprightly, youthful 49. Instead, what turns out to happen is she gets home and the Earth base calculation was right. 25 years passed back home, while 15 years passed on the spaceship.
But don't give away why.
I won't give away why yet, but this is why they call it a paradox. It's not a paradox because it's weird that two people who were born on the same day could now be different ages. Okay, fine, it's weird, but it's what happens. I mean, that is what happens. Again, we can't do it yet with people, but two subatomic particles that were created at the same moment are going to last different amounts of time if one of them is moving fast compared to your laboratory and the other one is not. But the weird thing here is they both seem to be doing their logic right. The guy on the platform seems to be doing everything right when he says 25 years should pass for me, so 15 years should pass on the ship. The person on the ship seems to be doing everything right when she says, okay, 15 years pass for me, so less than that, 9 years should pass for my brother on the platform. I will give you one hint. What she does during this story is flies that way at 8/10 the speed of light for a while, accelerates, turns around, and comes home.
Hey, Corey, we have seen Interstellar. In fact, we talked a bit about the physics of Interstellar on episode 2.
But you never let me rant about the characters.
No, I didn't let you rant about the characters. Okay, so I think we're going to wrap this up because we're trying to keep these to about half hour.
Answer to the twin paradox next time.
Yes.
It's not really a paradox. There is a resolution to that apparent logical contradiction there.
There is. Lily Blue, bye-bye. Corey, thank you for joining. So for those of you who don't know me, my name is Joe. This is Paul. I'm the physics program chair at Cabrillo College. Paul's one of our amazing instructors. We are here every Wednesday, 3 o'clock Pacific Standard Time, doing Ask a Physicist Anything. I myself am on here every single day. I made a 1-year commitment to share daily doses of dopamine through education, entertainment, and inspiration. Today is day 70. Okay, and then if you're around and you like physics, check me out on Saturday. I'm going to have hundreds of 4th grade students here. I'm going to have a bunch of liquid nitrogen. I'm going to show you 1, how you can solidify air, and then 2, how to make liquid nitrogen ice cream.
Awesome.
It's going to be good stuff. All right. My name is Joe, and this is Paul. Thank you for checking us out. And so go watch Big Bang Theory for next Wednesday. We have a homework assignment. Okay. Thank you all, Lily. Take care, and we'll see you hopefully next week.